זה קצת כמו קורס, כאילו הולך להיות עכשיו הוכחות כאלה דברים, כולם, טוב. אני אעשה הפסקה שיוכלו לעזוב מי שתבלבל.
שבוע הבא אני יוצא באיזה מקום אחר.
אוקיי. אני מקווה. כן, טוב. אוקיי. אוקיי. היי רמון. Okay, I think I'm going to start. Okay, guys? Okay, so thank you very much for coming to the second lecture in this 5 lectures mini course. Just before we start, so first of all, if you happen to sit in the back 3 rows, then please wear a mask, and masks are available if you don't have one over there. Second thing, so I understand that these are supposed to be 1-hour lectures, but I could be that I'll go a bit after 5. Don't worry. So my plan is to have a break at 4:55, and then anyone can leave without any penalty. And then at 5 minutes afterwards, those who remain will continue with me for maybe 15 more minutes if I need one. Okay? And those who leave, so I think I'll post lecture notes on my website. Okay, so even if you leave, you can look at the lecture notes and no serious harm. The first lecture, I have the slides. Okay. I can put my slides on my website too. Yes. Thanks for the suggestion. Yeah, good point. Okay, now, in each lecture in this mini course, for the first introductory one, the idea is just to pick a technique in convex geometry and just to explain the basic ideas behind this technique. And today, our subject is convex localizations for high-volume bisections. That's not a new technique. And I'm not sure that we'll reach the most sophisticated applications of each method, but the idea is that we'll see some applications and then the audience will be able to implement it in other situations. Okay. Now, last week we mentioned 2 inequalities from the 19th century. One was the Bourgain inequality, and the other was Bourgain-Minkowski. So let me remind you what's the Bourgain-Minkowski inequality. So Bourgain-Minkowski tells you that whenever you have any subsets A and B in Rn, so it should be Borel measurable, let's say, and some number lambda, then the volume of lambda A plus minus lambda B. I prefer the multiplicity fourth form because then I don't have to worry if one of the sets is empty. So this times lambda times the volume of B to the 1 minus lambda. This inequality is from 1887. It has many proofs. The first proof uses standard symmetrizations, and they are proved by decomposing into boxes and using induction number of boxes and the arithmetic geometric means inequalities are proved by induction and dimensions. There are many proofs. I'm not going to prove it here, although actually most of the techniques that we will see are strong enough to prove the Bourgain-Minkowski inequality, so you can view it as some kind of standing exercise whenever you see a technique. Let's see a corollary of this. By the way, whenever you want, please stop and ask questions or make comments, okay? I'm happy to have interactive.
Is there like a version with A plus B?
Yeah.
That's a little starting where to get there if you plug it in.
This is true, but then you have to assume that these are non-empty, and that's something that you always forget to assume.
Okay.
But it's true. Yeah, this is true also. Of course, it's lambda, and then this is true. Yeah, and okay. In this formulation, it should be to borrow n. Right. So this is better than that one. Yeah.
I think I'm used to the lambda equals 1/2 version.
Okay. Okay. So a corollary is the following: that if you have if x is a random vector which is uniform distributed in some convex set, and K is convex, and if you take some subspace E and project X onto E, then the projection is log concave. So log concave means that the density is e to the minus h, where h is a convex function. Okay, log concave looks like a Gaussian. That's log concave. Okay, what does it follow from the? Okay, so I mean, I put this corollary mainly to show that even if you only care about uniform measures in convex sets, log concave measures are likely to appear, for example, through this projection procedure. Okay, so the proof is not very complicated. So let's write f sub e will be the density of the projection. So what's the density of the projection? If this is k, and let's say that this is e, then density at the point x, what is going to be? It's going to be exactly the area of this section, right? So f at the point x is the volume of the section of k that lies above the point x, okay? And now, if I take 2 points, x and y here, okay, then by convexity, I know that if I take these two sections, so I know that k intersection x plus e perp plus k intersection y plus e perp over 2. I just do the like Ryan prefers, I just do the case where lambda is 1/2. So this is contained in what you get if you look at the section in the middle, right? I mean, so that's the section above x, the section above y, that's the section above x plus y over 2. And each point here, the average would be here. So you get that thing, and if you take the volumes, so this implies that the volume, that Fe, so if you take the volumes, you get that Fe at x plus y over 2, right, that's the volume of this thing, is larger than the area of the Minkowski sum. But if I use the Minkowski inequality in the multiplicative form, I get that this is at least the square root of the volume of this times the volume of this, which is Fe of x, Fe of y. Okay, so we see that this is indeed the log concavity condition. So we indeed proved that the projection is log concave. Okay.
When you want the quantitative log concavity, then what replaces? Is there any nice replacement, or can we get in this corollary?
So there are equality cases. There are convex bodies for which the projection, I mean, you have this with equality. For instance, a Q. Yes, so if you take a product, right, yeah. So this is at least tight. I can. There are, I mean, okay, there are local questions. So you know that the Hessian, so f of e is e to the minus h, where you know that the Hessian of h is non-negative. And there are expressions for this, for the Hessian of that, involving a few things, like the Hessian of the measure above and some infinitesimal transport cost of the fiber. There are some expressions of this, yes. Okay, but okay, but yeah, so I want to ask an advanced question. So let me just say two things. So first of all, not only the marginal of convex body is log concave, but actually, if you have any log concave distribution in Rn, then it is approximately the marginal of some higher dimensional convex body. Okay, so basically all log concave measures arise this way. And log concavity is a rather stable property. So for instance, if you have, I mean, proposition, this follows from Prekopa-Landler, which is a functional version of Minkowski. If x is log concave random vector, and you project it, it stays log concave. Okay, so then the projection is again log concave. Okay. Okay, I mean, you could say it follows from that if you begin with local given function and approximate it by some margin of higher dimensional convex body, and then you say, I project the convex body, so I get, or you can prove it directly. There are several ways to prove that. Okay, so locality is a rather stable property, and this is what Bourgain tells us. One more inequality from the 19th century that we mentioned last week was the Poincare inequality. And this was the following bound on the spectral gap. So if K in Rn is convex, mu, a measure of mu is low concave probability measure. And f is some smooth function, then let's say integral 0, then the L2 norm is bounded by, I do it with the best constant, so the diameter square over pi square. This was the pi, okay, that's maybe not Payne-Weinberger constant. Okay, and really that paper is the precursor of the convex localization method, as we said last week. Okay, so that's this was the Poincare inequality, and maybe you remember that there's equality if, say, in dimension 1, if you take K to be an interval and the function is cosine here, then you have an equality. That's the equality case. Okay, so the proof of this inequality proceeds by hyperplane bisections. Yes. Although, yeah, they didn't do it completely well, but yes, that's the idea of the original proof. Yeah. From 1960, 60 or 70? 60. Okay, so the proof we're going to use hyperplane bisections. So the basic idea is that if you have a convex set, and you take a hyperplane H and you bisect it, you get two pieces, and each of them is convex. And if you have a low concave measure here and here, then each of the pieces, and you restrict, will be again low concave. That's the basic idea. Okay, so let's fix some K, mu, and F as in the theorem. And let me begin with a little topological lemma. Okay, later it will be replaced by something like the Borsuk-Ulam theorem in more advanced applications, but for the first applications, we just need the following fact. So let's fix some subspace in Rn of dimension, let's call it E0 because it's not, of dimension n minus 2. Then I claim that there exists a hyperplane containing this E0 such that if I look at the two, okay, if I look at K intersection H plus of F d mu, or H minus, the integral will be 0. Both of them will have integral 0. Well, H plus and H minus, so if this is H, one piece is called H. So if this is hyperplane, called dimension 1, it divides the space into two half spaces. One of them will be H plus, and the other will be H minus. Okay, this is the statement. Of course, I assume the integral of F is 0. So the sum of these things is automatically 0, and the new claim is that each of them is 0. Okay, so that's a little lemma that we'll now prove. How do you do that? If I look at some unit vector, so I need to look at hyperplanes containing E0. So I need to choose a unit vector in the orthogonal complement. So for some unit vector theta in orthogonal, so this is a plane, right? So that's basic. I mean, the space of unit vectors is just a circle, right? This is the unit vector. I look at the hyperplane containing theta. Okay, so if I if this, suppose that E0 is just a point, we're in the plane. So theta is some. So this is h of theta, and I look at the following. I look at the two sides of h theta. I look at the difference of this minus h theta minus. With k, okay, all right. And the claim is that this function is odd and continuous. Yeah, I agree. Yeah, it's odd and continuous. Odd because if you switch, then right. I mean, they change, and continuous. I mean, yeah, I mean, because I don't know. Maybe f is smooth, so the domain convergence, something. Yeah, okay. Good, so it vanishes. So odd continuous function on this, and this is in a circle, right? I mean, orthogonal complement is basically a unit vector is just a circle, right? All things are odd continuous function on the circle vanish. Okay, so that's the elementary and elementary topological lemmas that will later be replaced by reversal Coulomb. Okay, very good. So we found we have this little lemma. So now what can we do? Excuse me. What's the question?
Islam is just saying you can cut this thing in half, more or less, right?
Weighted by f.
Yes.
Yeah. Okay. Now, so what it tells us is that basically. Yeah, no, affine. Thank you.
No, but in your, you don't need. I mean,
what, Roman? It's a trivial thing. Something we just miscommunication.
You could take all of K to be on one side of the hyperplane, and it would be too trivial, but wouldn't contain any information. Right?
Yes, okay, but I fixed. It's for any. So I fixed codimension one. This is true for any fixed codimension. So I need to choose wisely. What you say is that I need to choose later for the I need to choose it wisely. So if I choose a point which is not in the support, you can have something trivial. This is true. But I'm going to choose, of course, points which are in the support. So that's the.
I would have thought you wanted to center them somewhere inside the support.
Yeah, I will do that. I will do that. But that's for a fixed subspace. I will choose a subspace in a wise way. Okay, that's what's going to happen. More questions?
Yeah, vanishes means that this is zero.
Point where it vanishes. It's not a
Vanishes somewhere. Yeah, thank you. Yeah. It has a zero. Thank you. Sorry. Yes. Yeah. Yeah. Okay. So what's the conclusion of this topological lemma is that so we kind of we reduce the problem of proving Payne-Weinberger, which is one inequality on one convex set, to proving two inequalities of the same nature. So it's enough to prove separately for h plus and for h minus. So that we need to know that here. So we know that the integral of f, okay, we know that the integral of f on each piece is 0. And we need to prove that for each of the pieces, the L2 norm is smaller than the diameter. Let me even prove something stronger, the diameter of the piece, which could be in principle smaller. Square times the integral of the gradient. Okay. And now, if you do it recursively, so rather than you begin with your convex set, rather than the first step, you do this bisection, and then you take each of the pieces and bisect them. So maybe we get this piece and that piece, and again. So after k steps, you obtain a partition of up to measure 0 of your convex set into convex pieces. And the partition is what is the partition? the partition is k1 up to k2 to the capital N, let's say. And you know that for any I, the integral of f d mu I is, sorry, the integral of f over ki of d mu equals 0. Okay, these are convex partition. Into convex set, these are convex. Okay. Now, I want these pieces in the partition, I want them to be, I can claim that I can have enough I have lots of freedom, right? I have this to fix this, as Ramon said, I have this subspace that I can choose. So my claim is that I can use this freedom to force all of these ki's to be approximately one-dimensional. Okay, so we have the following. Let me first assume that the diameter of k is finite, otherwise there's nothing to prove.
Well, one-dimensional, you mean like one lower dimensional?
Sorry, what do you say?
You mean like really one-dimensional? You mean?
One-dimensional, yeah. So definition, okay, well, definition.
I mean, it would be good enough if they were like one lower.
So a convex set is called the needle, is delta needle for some number delta, if, actually I use the letter P for panicking because I have in mind things of higher dimension, but yeah, this will be, a needle is the one-dimensional case. If there exists some line L in Rn, such that P is contained in a small neighborhood of this line. Okay, and this is the Euclidean ball. This is unit ball. In other words, if I have this line L, I have its neighborhood, which is some kind of a, okay, you can, so this is the line inside, this is the neighborhood, and K is somewhere inside that. K is some, I don't know, this is a needle. That's what I refer to by a needle or a delta needle.
The ends are round, right? The ends of the needle are rounded, not the end of the line. Oh,
It's a line, it's a line.
Okay.
It's an infinite, it doesn't end.
Got it.
It's not a ray, not a segment, not a line segment, it's a line. Yeah. Okay, and the claim is that, yeah, after I assume the diameter is finite, that I can arrange, so we can find, we can choose these E's, E0, E1, etc., subset of codimension 2, such that the above holds, and everything is such that up to En. You can choose N. So for any delta, there exist N and subspaces of up to N of codimension 2, such that the above holds plus, and all pieces are, and all ki's are delta needles. How do you do that? You just, actually, it's not so complicated. You just take them to be proof or proof sketch. Okay, sketch, all right, need more. So just take some net, E1, E2, etc., in the space of, in the Fine-Grassmannian, in the space of two-dimensional subspaces, in the space of planes in Rn. Okay, and now, and the claim is that for large enough n, this just works. So why? So I take why does it work? How do I know that each of the pieces in the decomposition, all of them would be needles? So otherwise, I have a piece that contains some two-dimensional shape. Okay, suppose the piece contains a pentagon. All right, a pentagon. So it is a two-dimensional shape in Rn. It is inside the piece. However, since you have a net in the space of no, not a plane, codimension 2 of in the space of codimension 2 subspaces in Rn. That's an infinite sequence. Dense set. Yeah, a dense, sorry, thank you. Any dense set. Take a dense set in the space of, and then the claim is that if you have any two-dimensional plane, one of the elements in this dense set would intersect it, right? It's dimension, this is dimension 2. The other thing dimension codimension 2. So it has to intersect at some points. So, I mean, some point here. And now what you're going to bisect, at some point with respect to a hyperplane containing this point. So this means that you cannot have any two-dimensional piece that remains if you in this bisection. So for large enough n, you get delta needles.
So subspace means affine subspace.
Affine. Yeah. Affine. Thank you. Sure. Yeah, affine space, and take a point in somewhere in the center. No, something like barycenter. Yeah. So you get something close to it, and wait a second. Okay. So now we can prove Payne-Weinberger. So localization is a technique that reduces the proof of an n-dimensional statement to a one-dimensional statement. That's what we're going to do now.
The needles could just be like small and every, like a super small circle and a super small ball of needles, right?
Yeah, but note that the integral of f is 0 on each needle. Okay, for any I. All right, so if it's if it's very small, it's only where f is small, right? When f is, so we will not get so many tiny things because the integral of f should be 0. So it is the composition of all space into pieces, which are one-dimensional, let's say, and the integral of f is 0 on each piece. So there are regions, suppose that f is positive here and negative here, okay? It means that you cannot have any small circle here. It should go from the right side to the left side. So it should be, it's a macroscopic segment. It's indeed a needle decomposition. That's the picture to have in mind.
So it's actually one-dimensional, not two.
It is, there are degenerate cases, right, as you said. Yeah, this is also a needle, right.
Yeah.
But most of, near the 0 set you can have such things. If this is the 0 set, yeah, you can have things like that which are small. This is true. But other than near the 0 set, in the bulk of the space, no, it's macroscopic. Okay, so let's prove Payne-Weinberger. So let's assume that K, we said K is finite diameter, it's compact, good. So let's assume that F is smooth. So F and its gradient are uniformly continuous. Yeah, thanks. Yes. So they're uniformly continuous, and let's pick some epsilon greater than 0, and let pick delta by uniform continuity. Okay, and apply this needle decomposition. So we apply the old machinery as we said earlier. We have this delta. We take not a net, a dense set, sorry, a dense sequence in the space of conscious spaces. We truncate at some point. Then we do the little topological argument. And we get a partition of this sort, okay? And it's enough to prove that for any I, the integral of f squared on the piece is smaller than, I'll put 1 plus epsilon because, times the diameter of the piece, the integral of the gradient of f squared. Okay, now we use the fact that so far we haven't used log concavity at all. So now we're going to use it. We're going to project. So we know that K. We know that Ki is a needle, is a delta needle. So Ki is contained in some Li plus delta Bn, where L is some line in Rn. So let's denote. So rather than working on the needle, basically you can project everything to this line. Right? The needle is just a little approximation of this macroscopic line. That's what I get. So let's let's denote by nu I the projection onto Li of the push forward of the measure restricted to Ki. So this is low concave, because when you restrict low concave to a convex set, it's low concave, and this is by Prekop-Allender or Bourgain-Minkowski, low concave again. And now the function f is uniformly continuous, so it does not, if you move from a point on L to its nearby point in the needle, f does not change by more than epsilon per choice. So what you get is that it suffices to prove the following. Thank you. What you get is that it's enough. So what we need to prove the following, that for any segment I, no, let's do it this way, that for any G, okay, we have the Li, so we have the nu I, to prove that for any smooth function G, if the integral of G with respect to nu I is 0, so nu I is a measure on L. It's a measure in one. Is a measure in nu I is 0. It's a measure in one-dimensional line. Then the G squared in nu I is smaller than the diameter length of okay. So the interval II is K intersection with Li. So it will be the diameter of II square over pi square. And you know, I'll write G prime and not gradient of G because I only have one direction. It's a bit, no need to write the nu I. Okay? So this is what I want to prove, and there's no epsilon here. That's what remains to be proven.
You're just taking the restriction of the measure to the set Ki, so it should just be the density of the original measure on the set Ki.
Yes, but that's the first step. Then I project it orthogonally to Li. So this is the Li. The convex set is some neighbor. It's, say that, I don't know, this triangle. This is Ki. All right. So I take the push forward of the measure. Maybe I should put a star or something. Would it be better if I put some hash or star or something? I push forward the measure here via the projection. So for example, if it was the uniform measure on this triangle, the projection would be a measure on a line whose density is like this.
But in principle, you could just take the limit as delta goes to 0, and then you would just get the restriction of the density to the line. Because the difference between this projection and the restriction to the line should...
Okay, I'm not sure I'll take the limit. Yeah, there is a limit object, we'll discuss it next week, but in this formulation, it's not so clear how to take the limit because we have some topological choices and there's no consistency among... Okay, but all right, yeah, I take the projection and this is what I need to prove. Okay, so now this is already, now I stop pretending that in n dimensions. Now this is a one-dimensional problem. So now we are done with the convex localization part. Let me put some interval I everywhere. Let me make the interval 0 pi. By scaling, you can make it 0 pi. Okay. And we just need to prove some inequality in one dimension, that whenever you have a function with integral on 0 pi with respect to some measure on u is 0, then the same thing. And there's no constant, that's what we need to prove. Sorry?
There's no constraints on integral 0.
G, function G, there is a constraint, you should have integral 0. Okay, so the claim is that integral 0 pi. Okay, let me just rewrite it. That for any G, say smooth or something, if the integral of G on 0 to 0 pi is 0, then the integral of G square is smaller than G pi square. Okay, now this is a problem that this is related to Sturm-Liouville type problems in ordinary differential equations. And there is an operator. So this is a spectral graph problem for some operator. D nu. Sorry, D nu everywhere. Sorry. And nu is low concave. So nu as density e to the minus psi, where psi is convex. Okay. Now, this inequality amounts to spectral gap for the following operator. So this is a Dirichlet form. You can write it as the integral of minus LG times G for some operator L, which I'll write now. So what we're going to be L? Okay, I'll write it here. So right, so the form is G prime square e to the minus psi. This is the form. So it means that L of G is if you do integration by parts, you want to take G prime e to the minus psi and differentiate it and multiply by e to the psi here. So it's G double prime minus psi prime G prime. Okay, this is the operator L. Okay, and so we know that L of constant is L of 1 is 0. It's self-adjoint with respect to okay, it's self-adjoint. So so L is self-adjoint where? L is self-adjoint on the domain which is you take all functions G that are absolute continuous and the derivative absolute continuous, and L of G is square integrable, and G prime at 0 equals G prime at pi equals 0. It's self-adjoint on this space.
Can't you just write out the Taylor series of G, like if G is sum of A and sine and theta plus some B and cosine theta?
So if psi would be constant, if you would work, if the measure would be uniform measure, then you're right. Okay, that's a good remark. So if the measure, yeah, a good point is that if the measure is the uniform measure on the interval 0 pi, then you can solve it by Fourier series.
Yeah.
And then it just works, right? You know that the spectral up is 1 and cosine is the extreme. However, you have some density. Maybe the density is this function. Okay, let's assume that it's smooth, it does not vanish at the origin, but I have some density, so I need to do something. So there's no explicit formula, there's no simple explicit formula for the eigenfunction, for example. Okay, now, so there is a nice transformation. Okay, right, so this is the domain of G, so that makes it self-adjoint, and you need to prove that it has a spectral gap. So there's a nice transformation, which is, so the following transformation, so T of G is e to the minus psi over 2G prime. And this, we use this to conjugate our operator L. This transformation, if you've never seen it, looks a bit strange, but there are two things to note. So first of all, it's self-adjoint in L2 of no. So if you multiply by e to the minus psi over 2, this is an isometry from L2 of the Lebesgue measure and L2 of no. And if you just look at G prime, this transforms the Neumann Laplacian or the Laplacian in the case of the uniform measure. So if you do this for both of them together, and you write, and you see what would be the conjugate of L under this operation. So you want an operator such that if you look on so I want to define L, so A, so that applying that AT would be, so I don't want to write T minus 1, I write T times L. This is what I want to do. So what is A? Let's try to understand what is A here. So A of some function G, what should it be? So I know that, or should I do it this way? No, I want it this way. Okay. So what do I want to happen? So suppose that G is T of some function, and then I want it to be like L. So I want to take so all that remains to multiply by e to minus psi 2 of G, right? And then differentiate this and multiply by e to the psi. But then I need to apply T for that. Right, so this should be, did I write it? Let me check in my notes. I think I'm confused a bit. So, yeah. So times e to the minus psi over 2. So this happens if you conjugate this thing. Okay, and I'll just write. I mean, I think that we cannot. So what you get is that your operator is conjugate to this Schrödinger type operator. There's no constant term. Right? I mean, let's see. So if I put a of t of g, then I get e to the minus psi g, which is differentiate once. I multiply by e to the psi. Then I need to no, a to the t is t of l. Yeah, that's what I wanted. Right. And then I apply t again. Yeah. This is so I'm sure about that thing. And this apparently I copied from the page, but you can make this computation yourself. Okay, and now finally we can use low concavity. So we know that psi double prime is positive. So we know that all of these things in the box is positive. So this means that our operator A, which is conjugate to L on the space of function of integral 0, so A is at least the minus of the Dirichlet-Laplacian. Okay, and the spectrum of Dirichlet-Laplacian, as people told me here, is known, is 1, 4, 9, 6, it's squares, right? So we know at least the first eigenvalue is at least 1. Okay, so since this operator is at least, it's the Schrödinger operator with a positive potential, and the potential is at least, so it's at least the thing, and you get that the spectral graph is at least 1. Okay, so I was a bit sketchy about the ODE part of the proof, but I think I did carefully at least the convex geometry part of the proof. Okay, so this is Payne-Weinberger. Yes, please.
So it's not possible to apply this spectral theory.
Discrete spectrum, what?
This, spectral gap argument already at the higher dimensional.
Yes, there is a Bochner type, exactly. So in the third lecture, we'll see a Bochner, yeah, there is a way to, not exactly, so there's no, okay, this transformation is just in one dimension. So there's nothing so simple can work in higher dimension, but there is a Bochner type argument that can prove that thing, but it's of different nature, I think.
So if your partition would partition it to things of smaller diameter, things would be better, right? So somehow, can you tell in which cases you are forced to have things?
Yes, for instance, if you know that your set is isotropic, if your measure is balanced in all directions, the covariance is identity, then you gain a factor of n over the diameter squared, typically up to some log factors. So this is the Kannan-Lovasz-Simonovits conjecture, which is the result. So if you know that your set is balanced, the worst case is if you have segment. But if you decompose in the isotropic case, the needles will be much shorter. There will be, if they say, I don't know, take a unit cube for instance, then you would expect the diameter to be root of n, but the needles will be something like 1 in that for the unit cube or for the unit ball or for things which are isotropic.
Some of the bad cases when it's, for example, one-dimensional to begin with.
One-dimensional what? Cube.
To begin with, it's
Yeah.
one-dimensional.
Yeah, that's the, yeah.
But boss, just so I understand correctly, I mean, what Noga is saying is asking about when you do this partitioning, whether you can have situations where the diameter will shrink. But you're not claiming that if you have an isotropic situation,
sure.
then when you're applying this
Yeah.
the diameter will necessarily shrink?
So I claim that there is a decomposition for which the diameters are shrink. Yeah, I don't claim that all. Yeah, I claim that there exists a decomposition that the diameters shrink. Yes. Yeah. I know how to find it. Well, there is this optimization problem. Okay. All right. If you optimize the L1 transport, it will do that, for instance, the L1 cost. Okay, so this was first application of integral position. It's a bit took me more time than I expected. The second application is Gromov waist inequality. So that's the following theorem. So first of all, the Gaussian measure. Gamma n is the Gaussian measure in Rn. So the density is e to the minus s squared over 2 over 2 pi to the n over 2. That's the density. And the theorem says the following. So for any continuous function f from Rn to Rk, there exists a large fiber. There exists some number t. So k is any number, k and n are any numbers, k smaller than n. So exists a fiber, maybe n minus, I mean, I'm not sure if, well, probably it's okay also in the borderline cases, such that if you look at the fiber L, which is f minus 1 of t, this is a large fiber, okay? In the following sense, for any number r, if I look at the r enlargement of L, L plus RBN, and I look at the measure of this enlargement is at least what I get for Rn minus k if I put here. Like if I take the case where f is a linear function, I take the fibers through 0. Okay, this thing better to write is just as gamma of k of RBK. This is what it means. Rk is the subspace of any subspace of Rn through the origin. Okay, let's draw the picture. So this is Rn, and we claim that there is some fiber L. Okay, typically it's of codimension n minus k, right? And they claim that it is large enough in the sense that if I take the neighborhood, the R neighborhood of L, then it's always larger than what I get if I take flat thing. So this is larger than what I get if I'll take a flat thing through the origin and take its enlargement. Okay, so f linear is a quality for linear f. Let's put it this way. Okay, and before proving this theorem, I say a few words. So first of all, there is a major difference between the case k equals 1 and k which is larger than 2. So for k equals 1, this is from 2 to 2. For k equals 1, this may be proven by many ways. It follows from the Gaussian isoperimetric inequality. For k equals 1, this is a scalar function. So you can take t to be the median of f. If you take t to be the median of f, you divided Rn into 2 parts of measure 1, I mean, typically measure 1/2, okay, for typical function f. And you know that, if it's the partition of 2 measure 1/2, you know that the boundary is large enough, and there are extremal cases when you take hyperplane sections through the origin. So for k equals 1, you know that t is the median of f. And moreover, for k equals 1, most of the mass lies in large fibers. So most of the mass of the Gaussian measure lies between the quantile 3/4 and the quantile 1. I mean, half of the mass is between these 2 quantiles, right? I mean, by definition. And anything in any level set in between would have very large measure, right? Because it partitions the space into roughly comparable pieces. Okay, so most of the mass lies in large fibers, and you can expect probabilistic proof, probabilistic arguments. However, this for k larger than 2, this is unfortunately a theorem about Gaussians. It is not probabilistic. It's not probabilistic because most of the mass could lie in small fibers. So there is an example of Alpert and Guth showing that, you can have situation where you actually find a needle in a haystack. No, okay, that's needle, yeah. That there is just kind of one large fiber, okay, that has large epsilon enlargement, but most of the mass is in tiny. The other fibers are just tiny, but there is at least one big, so it's kind of a pristine fiber. Okay, more things to say. So first of all, there is the following notion, So you can be more low. So mu, I measure mu is more low concave than the Gaussian. This is terminology that we will use. But it puts some, I mean, okay. If in the smooth case first, in the smooth case you want d mu to dx, it's e to the minus psi, and you require that not only the Hessian of psi is non-negative, you know it's non-negative by just low concave, but you require it's larger than the identity matrix. If it's the Gaussian has this property, standard Gaussian has this property that it's logarithmic Hessian is the identity matrix. So if it's more low concave, the Hessian is larger than you say it's more low concave than the Gaussian. That's in the smooth case, and in general, or requires that, if it's not smooth, it requires that psi plus minus x over 2 is still convex. That's the definition in the non-smooth case. Okay, so if the Gaussian measures look like this, then if you're more concave, you expect something like this. I mean, you curve more than the Gaussian. Okay, and in fact, we'll prove a variant of this theorem where you can put here mu. So this is true. So if you can put here mu if mu is more low concave than the Gaussian. Okay, this is a theorem about convexity, not about symmetries of the Gaussian or anything like that. And more remarks, so there are variants of this thing in convex geometry. So Gromov proved the waist of the sphere theorem, which is proven in a similar way. So function of the sphere, you can do it. It's true also for the Euclidean ball. This was deduced from the sphere very easily by Koppen and Karasev. There's a version for the cube. It's sharp. And there are also non-sharp versions for general convex sets. But for the cube, ball, and sphere, these are sharp versions. Okay. Questions or anything about that?
So in all these different versions, it's the domain of the function that's changing? Like for the cube?
Yeah, the measure. The measure can be Gaussian. It could be uniform on the cube. Or it can be uniform on the Euclidean ball, or uniform on some convex set. Yeah. Or the domain of the function. You can think about it this way. Yes.
What's an idea of the application of this result? Is it happening?
Good question.
Isoperimetric theorem has millions of them.
This is true. This is true. It's a good question. You can prove other waist inequalities using that thing. Actually, I don't have kind of a clear killing application for this thing. Gromov used that in. You could, I mean, first of all, it's relatively recent. I mean, it's not as old as the Gaussian probability inequality. It's from 2000, right? But yeah, this is legitimate criticism, right? I don't know any super application of this inequality. Okay, so I think that I will take a 5 minutes break. Okay, and we'll continue at 5. These are questions. No, you can. Okay, whoever.